Oh, yeah, and then you're never gonna see yeah, that's I'm excited for Black Ops. It's so hard to like. It feels like Black Ops.
There we go. All right.
I wish it was man, that's too realistic. You play Rainbow Six.
Who doesn't play Rainbow Six?
I don't. I think there's really
Fair enough.
I prefer to play games that have stress.
Found a video about Rolina.
Yeah, watch a little bit.
Rolina? Not saying I did, not saying I did.
Now I'm sad. I thought you came up with
Rolina. All right. Say what? All right. So if you're still working on the lab, try to get that done. Move on here. All right. So example number 4, we're going to be talking about projectiles at an angle. We're going to nail it. All right. We're going to be talking about projectiles. Ooh. My thing's not even working anymore. Come on. Come on.
I'm
literally I have so much. Like it's not right now, but it's just like I'm just ready.
What's it about?
Image made.
He is my
Right now.
There we go. All right. So we are going to do example number 4. Oh, that's not even 4. There's number 4. I did skip 3. We know horizontal. We're good with horizontal. We're going to angles. Let's see. I'm going to tilt this way. Zoom in a little bit. All right. So let's see. There we go. All right. Now, there we go. All right. Unable to leave the cubs helpless, Rolina decides to make pumpkin soup for the cubs. In the middle of the night, some wolves come looking for food. To get rid of the wolves, Rolina throws a pumpkin 1 meter from the ground at an angle of 30 degrees with a velocity of 15 meters per second. The pumpkin takes 1.62 seconds to hit the ground. Calculate displacement in the x direction. Wow. That's a lot of information they just gave us there. That's pretty nice, right? We were just given so much information. All right, so what I'm going to do is I'm going to create a little XY chart. Let me see if I can move that a little bit. I'm going to create my XY chart just so I can analyze the data that I know. Okay, so in the x direction, well, I know my acceleration is just going to be 0. But my acceleration in the y direction's gravity. Well, that's pretty easy. Time is the same for both of them. My time was 1.62 seconds. Time was 1.62 seconds. Okay, it's not too bad. What else do they tell us? All right, so if we look at this picture, she let the pumpkin go 1 meter. All right, so it actually falls 1 meter in the y direction, right? Based off this picture. So my delta x in the y direction is -1 meter. All right. Do we know anything else?
Oh, the initial velocity?
At the ground at angle with a velocity of 15 meters per second. Well, yes. Okay, so let's draw a picture out here. So what I got is she launches it at 15 meters per second. The angle at which she threw it was said to be 30 degrees. All right, so I need to find the x and the y, and that'll tell me the initial velocity of both of those. Okay, yeah.
Okay, so if you were to do this with drag, would I just change the acceleration in the x direction?
Basically.
Okay.
Yeah.
But how would I find the acceleration induced by drag?
We're not going to get there.
Okay.
All right, so we're going to use the good old trigonometry. So, ka, atoa.
What do you say?
Because why not? So, katoa.
There we go.
All right, so what I'm going to do is so. All right, so the sine of 30 is equal to the opposite over the hypotenuse, which is 15. Let me grab a calculator real quick. Let me zoom out so you guys can see what I'm actually doing. There we go. Can you guys see that all right? It's kind of small. Let me zoom in a little bit. Is that better? There we go. All right, so sine of 30 times 15. I got 7.5. All right, so my initial velocity in the y direction is 7.5 meters per second. Beautiful. Okay, so the cosine of 30 is equal to the adjacent over the hypotenuse. Cosine of 30 times that by 15. I got to be 12.99. I'm going to go 13. Okay, initial velocity is 13. Any questions on that so far? Okay. Now, the question says, find the displacement in x. Okay, so I got to find the displacement of x. So how far did this actually travel? Okay, so I got to find x. Okay, so the equation I'm going to use is the delta x is equal to the initial velocity times t plus half the acceleration times squared. Now, since I'm solving for x, I'm just going to use my x data. Okay, so my x data is delta x is equal to the initial velocity, which I just said was 13, times the time, 1.62, plus half the acceleration. What's the acceleration in the x direction? 0. So it's just, that's all I got. All right, so when you plug this into the calculator, I got 21. Got 21 meters. Does that kind of make sense?
That makes a lot of sense.
Yeah.
Not too bad. Kind of similar to what we did, except instead of doing straight horizontal, now we got to figure out the x and the y. Okay? So what I'm going to do, I'm going to tear this off so I still have my data because I don't feel like rewriting all that data down. All right. So I'm going to keep all this. All right, so what is the maximum height? Okay, or what is the speed? Oh, what is the speed at the maximum height? Okay, so if I look here, there's going to be my parabola, right? Up here, what is the speed in the y direction? 0. Now remember, in the x direction, velocity is constant. Wait a minute, I already know my initial velocity. So if velocity is constant, my speed is going to be 13 meters per second. Well, that's an easy question right there. I already have all my data. Say what?
Would we ever have to be like, what is the speed at like 1.6 seconds or something? Like interval that's not at the top of that.
Yeah.
Would we have all the data that we need?
Yeah.
We can plug it into equations basically.
Yeah.
Sorry.
Our next question will ask that. All right. Great question. I love it. I love it. All right. Next one says, what is the speed when it hits the ground? Okay. What is the speed when it hits the ground? So I have to solve for final velocity. Okay. So let's see. All right. Looking at all our data, what is the speed when it hits the ground? Okay. Now, I know my initial velocity in the y direction. Okay. I know the time it takes. I know the acceleration. So let me find. So I got to find this. Okay. So I know, I'm going to draw this a little bit bigger. I know my velocity in the x direction was 13 meters per second because that never changed, right? But now I have to find the amount of fall, the velocity final for x. I got to find my velocity final, or for y. Holy smokes, for y. Okay, so I'm going to use the easiest equation. So acceleration is equal to the velocity final in the y direction minus the initial velocity in the y direction over time. Okay, so I know acceleration in the y is negative 9.8. I don't know my final velocity. I know my initial velocity in the y. My initial velocity is 7.5. And I know my time is 1.62. Yep. Look at all my data. So my VF, okay, so I'm going to multiply negative 9.8 times 1.62. Oh, not 162. 1.62. Yeah, was that back there or down? It did sound expensive. Good thing it wasn't me, you know? All right, and then add 7.5. All right, so I got about 8 point.
Excuse the interruption. McKinley Earhart, would you come to the attendance office, please?
I got about 8.4. Is that what you guys got? All right. So what is the speed? What you got to do is find the resultant vector, right? Oh, there we go. Got to find the resultant vector. How would I do that? Yeah. Yeah. How would I find the resultant vector? Pythagorean theorem. A squared, so 8.4 squared plus 13 squared. Oh, squared. And take the square root of that answer. I got about 2 sig figs, 15 meters per second. That's what I did. Yes. Be negative 8.4. Does that kind of make sense? Yeah.
Can you use the Pythagorean theorem when it's like hard? It's not really a straight line.
You're figuring out. You're correct. So, see, that did not sound expensive.
Yeah.
So, you have your vertical down, vertical. Yes, essentially it does curve, but we're just mainly finding the total distance. Yeah.
But wouldn't it be because it's in meters per second, it's not actual distance, it's the speed at that instant in time?
Right.
So it would be a straight for the triangle. It's instantaneous velocity, not velocity over time.
Yeah. Yeah. All right. Next question. All right. This gets to where Aiden was talking about. All right. Next question is a little tricky. As the cubs start to get older, Relina has to find ways to entertain them. The cubs love to chase rocks, so Relina kicks a rock, sending it 3 meters over a 3-meter high tree. But like the rock god, do you remember Rogar?
It's Roger.
Roger.
Why isn't it
Roger,
named
my
after-
bad. Say what?
The line in.
All right.
Into your spot.
So it's over a 3-meter high tree that is 14 meters away. The rock lands at the same level from which it was struck after traveling a horizontal distance of 17.8 meters. Wow. Okay. Once again, a lot of data. The rock, if the rock left the ground 54 degrees above the horizontal, okay, 54 above the horizontal, and landed 2.24 seconds later, what was its initial speed? Okay. So let's see all our data. We got a lot of data here. All right. So I'm going to write my X, going to write my Y. There we go. Don't need this paper anymore. Got my X data. I'm going to put my Y way over there because there's a lot of data to write down. All right, so acceleration in the X is always going to be the same. We have acceleration is 0. Acceleration in the Y is negative 9.8. Okay. Let's see, what else do they tell us? So the total distance X was kicked, the total distance or displacement was 17.8 meters. Okay. Let's see. The time was given. So the time was 2.24 seconds. 2.24 seconds. Now that is the same for both of them. Okay. Let's see. What else? What's my displacement in the Y? 0. Right? In the Y, if it's kicked, it goes up and it goes down. So the displacement total is going to be 0. Okay. Now, let's see. So when she kicks it, we know it's at a 54-degree angle. It's at a 54-degree angle. Okay, we know that. Let's see. If the rock landed, what was its initial speed? Okay. So first, what we're going to be doing is we're going to find the displacement. Let's do X first. Okay, let's do X. So I got to find of X. So delta X is equal to the initial velocity times time plus half the acceleration times squared. Okay?
Wait, why are we finding the displacement if we already know the displacement? Oh, wait, wrong one. Yeah, if we already know the displacement of 17.8.
We're finding the initial velocity.
Oh, okay. Sorry, I got lost.
You're good. You're good. Yeah. All right. So initial velocity. Well, delta X is going to be my 17.8. All right. Initial velocity, don't know. My time, I do know, which is 2.24. And then the rest, once again, acceleration is 0, so I can just cancel that. All right. So when you divide that over, my initial velocity is going to equal, I got 7.95 meters per second. So that's the initial velocity in my X direction. 7.95 meters per second in the X direction. Okay. Is there a way? Do I have to solve for the Y direction, or can I just solve for the resultant right away? Yeah, I can solve for the resultant, right? So I know the adjacent angle, and I'm solving for the hypotenuse. So I'm going to use cosine. right? So the cosine, you can see it. So the cosine of 54 is equal to the adjacent over the hypotenuse. Correct? Okay. And then when you solve for h, you're going to have 7.95 divided by the cosine, 54. I got 13.5 sig figs 13.
It should be 14.
Oh, 14. Yeah.
Why is it cosine?
Cosine, because we have our adjacent and we're solving for the hypotenuse.
Oh, okay.
Yeah. Yeah.
Why would it be if it's like a parabola, why are we solving for like almost a straight line?
We're just solving for the initial speed.
Okay.
We're not solving for like the entire, like really, we're looking for like that immediate takeoff.
Got it.
Like the very tiny.
It's instantaneous.
All right. Now, how high was the rock when it passed over the tree? Okay. There's a lot of things here. All right. A lot of things. So how high was the rock? All right. So once again, we know A is equal to 0. Oh, yeah, you can see that. A is equal to 0. We know X. Well, how far is the tree from us now? 14. So A is equal to 0. X is 14. I know my, let's see, what do I know? What else do I know? My initial velocity was 7.95 in the X direction. Or, yeah, 7.95 in the X direction. Okay. Let's see. Time. Do I know my time? Not yet. Okay. All right. So I think that's all I know for now. All right. What you're going to do is, I have my drawing over here. I'm going to use the same drawing. Okay. So if I do a squared plus b squared equals c squared, I can see the height. Okay. So the height of this is going to be, let's see, this was 13.5 meters per second. A squared plus b squared equals c squared. Take the square root. I got the height to be 10.94, around to 11. Okay. So the height of that is 11. All right. So that's my initial velocity in the y direction. Okay. Acceleration is still negative 9.8. All right. Let's see. And that's all I know. Okay. So first, we're going to solve for time. This is a big problem. This is a big, big problem. All right. I'm going to need another piece of paper. So you might be writing small on this one. All right. So that's what I know so far. Okay. Now I have to solve for time. So what I'm going to do is I'm going to use the delta x is equal to the initial velocity in the x direction times time plus half the acceleration time squared. There we go. Okay. So my delta x to the tree is 14. My initial velocity is 7.95. I don't know what t is. I'm solving for my time to see how far it is. My acceleration in the x direction is just 0, so I can just get rid of that. So to get my time, I just divide it on over. So t is equal to, right here, I don't need to worry too much about sig figs. I got 1.76. Okay, so I know my time now. Time is 1.76. Time is 1.76. Does that make sense so far? So what I'm trying to calculate is how high was the rock when it passed the tree. So I'm trying to solve for delta x in the y direction. Okay, so what's my delta x in the y direction? Well, I have a lot of data. If I know my initial velocity in the y direction, and I know my time plus half the acceleration time squared. All right, this is going to be a lot of math right here. Initial velocity in the y direction, I know that to be 11. Time, I know to be 1.76. Plus half, what's acceleration in the y direction? Okay, times time squared. Bada bing, bada boom. Hot dog. Okay. Did anybody plug that all in? Yeah, what'd you get? 4.18. It's going to be, well, you add, so yeah, 4.18 is perfect. Units meters. Okay, so that's.
How do you know that that's what we would be finding for this displacement in the y direction? How do you know?
Oh, how do I know? How high was the rock when it passed the tree? So when I'm trying to see, so if I have a tree right here.
Oh, all right.
So there's my tree. I'm just finding how high it was at that instant.
All right.
Oh, you can't see my beautiful drawing of the tree? I drew a tree right here. I just did right now. So I was finding how high it went.
So that's somewhat makes sense.
When you
explain it, it makes sense, but like when I have to like think about it, I'm gonna.
That's fair. That's why we're practicing. All right. What is the highest point reached by the rock? So I'm trying to find its very highest peak. All right. The very, very highest peak. So got to look at the data I know. So all I'm worried about is the y direction. All I'm worried about. Okay. So let's look at my y information. All right. So I know acceleration is negative 9.8. All right. I know my initial velocity in the y direction. That was, where did I write that down? 11 meters per second. Thank you. All right. What would be the time? Do I know the time here? 1.12. How'd you get that? So it's half the time, right? It's half the total time. So half the total time would be 1.12 seconds. Does that make sense? Okay. And let's see. What's my final velocity? What's my final velocity right here at the very peak? 0. Okay, I got a lot of information. Let's see, what equation can I use if I'm solving for x, delta x? I'm going to use the velocity final squared is equal to the velocity initial squared plus 2ax, x in the y direction. Does that sound good? All right, so velocity final squared. So 0 squared, that's pretty easy. Initial velocity squared plus 2 times negative 9.8 times x in the y direction. Okay, let's see. So I got 11 squared, 121. I'm going to subtract that over. So I got negative 121 is equal to negative 19.6 xy. 19.6, 19.6. All right. So 121 divided by 19.6, I got to be about, let's see, 3 sig figs, 6.17. X in the y direction, 6.17. Yes.
Couldn't you have just plugged 1.12 into the equation that you used in part B?
Delta y equals initial y plus t You could. Yeah. Yeah. All right. So that's all we're doing today. What we're going to be doing on Monday, I'm going to be launching a ball right here.
You're hitting monkeys.
You're going to hit monkeys.
Well, you said that we were.
I did. I was going to try to get a one-eyed lion in here. But what you guys are going to do is you're going to be calculating the height of this based on the distance it travels, the angle it's at, and the time it takes to land. All right, so we're going to be doing some launches.
This sounds like math with extra stuff.
That barely misses the ceiling.
I've been practicing.
It barely misses hitting the wall.
So, is there any questions? Yes.
Happy goal.
That's fine.
How many counts?
All right.
Yeah.
So,
That's a good question.
Yeah. Can you put it in so we don't do much helping?
Yo, shoot Jenkins.
Yeah.
Yes.
Public execution.
hold on. We'll try it.
Jenkins, right, prongs against
I gotta get it out.
I sent it to Kennan.
I'll get that in a second. Jenkins, you want Jenkins to be shot?
Yeah.
Off with his head.
My bad.
Up with his hide.
I don't think it's gonna fit down in there.
If you put the ball in and then put Jenkins,
Yeah, you make it savage.
you could make it shoot out.
Yeah.
I have to cut off the zero.
It's worth it. He deserves it.
Should I do it real quick?
Put the ball in and then put the
Ball then Jenkins?
Because then the ball will shoot out.
It took you forever to find him, so I'm sure that he's hit the same.
I am too. I've studied all.
Oh, I've still got two.
I'm going to Broadway, so
Yeah,
we'll be fine.
Oh!
What?
Close the door, close the door. Execution.
Oh! Oh, his nose got stuck. Oh, got his stuck.
Jenkins made a cross against humanity.
We'll work on it Monday.
Have a nice weekend.
You too.
I didn't get bonus point there.
You just get stuck in there.
What if you flip him around, like put his head facing the other way?
Hold it a little bit.
Yes.
All right, let us stop presenting here. X. Oh, there we go. Let's see. Stop recording. Beautiful.